Actually, for those exam quizzes one or two, I actually sent a mail to him that I would appreciate if he could post solutions to the questions because of I just needed to know because of my performance, in
Right.
quizzes one or two. So I just needed to uh, know where I didn't get it right.
Hmm.
But uh, but he posted the answers, and it's okay though. Even though he didn't post the solutions, but he posted the answer. It's okay. At least it gives me room to work and see where I can how I can work the questions and get the answers. You know.
I see here he put, at least on the first one, he has the question and then the answer is right here
hmm
at the end. Is that what you're talking about?
Yeah, I actually thought he was going to work it out and send the how he ar- how to arrive at the answers, but it's okay. I mean,
Oh,
it's
I
good with me.
see.
Yeah,
Hmm.
I'm good. I'm okay. At least I can. I have to go and you know I'll go back to my books and see if we can work it out together. You know.
Sure. Would you like to work on any of the problems from quiz one or two today?
Yeah, maybe we should just look at them because there are about five questions. I don't know if you have the time. We could just look at both quizzes. Maybe we'll start with um, quiz one or
Quiz,
two, whichever one is good for you or you're okay with you.
I'm okay with both of them. And I have all of my notes here in front of me for all this stuff. So, you said quiz two, like the chapter five material?
Mm-hmm.
Okay.
Yeah.
All right. So, so first of all, this test is over chapters two, four, and five. That's
Mm-hmm.
correct.
Mm-hmm.
That is 1D motion, 2D motion, and net force. So, okay, yeah, this quiz two, quiz one is, I believe, 1D motion, or possibly 2D motion, or both, maybe, I can't really remember. But this chapter two is particularly important because it's chapter five, net force, which is very important. Um, so yeah, it's a great idea to work some of these out. Um, Let me see how many there are. Okay, four. So we should definitely be able to get through all these. Wait, sorry, five. There's five. So yeah, we can definitely get through these. Um, and then at the end, I'll recap the kinematic equations if I have time.
Mm-hmm.
Just since this is kind of a general exam one review, but chapter five is extremely important because it's where a lot of misunderstandings start to occur. 1 and 2D motion are particularly straightforward. Like their ideas make sense, how things move and everything. Motion can be a little more tricky. So let's start with number one. And hold on, I believe I have um, these things written out here. Actually, for another student in another class, I've worked out, I believe, this entire quiz. So let me just pull that out really quick. Okay, so first is two ropes are attached to a 40-kilogram object. The first rope applies a force of 25 newtons and the second 40 newtons. If the two ropes are perpendicular to each other, what is the resultant acceleration on the object? So, first off, that may seem, sometimes these questions aren't always super clear, one may think. Like, what I mean is, like, when I read that, um, I was like, the two ropes are perpendicular to each other. Like, I mean, I know what perpendicular means, but like one going to the left, one going to the right. how are they oriented? The fact of the matter, I looked this up on the internet, because at this point, looking things up on the internet, like if you want to learn how to do things, it's not cheating. It's like trying to learn how to do these things.
Yeah.
So the diagram that they drew looks like this. So it says the two ropes are perpendicular to each other. Perpendicular means at a 90-degree angle, like so. So for the sake of this problem, it's pretty like just simple. It's not complex. So you can just draw one like this and one like this. It doesn't matter if they're going, if maybe this one was over here. That is not really the big idea here. The idea is that they are like so. And one of them has 25, the first rope. So first one has 25 newtons of tension. And I think it's important to point out force is newtons, which is, I believe, kilograms per meters per second squared. And that means that it's a mass being pushed with an acceleration. That's why net force is equal to ma, the mass times the acceleration, because its unit is the newton, which means kilograms times meters per second squared. And as you can see, that breaks down into the mass and the acceleration units. So, tension, I was saying, is if you were to push this box, like with your hands or with, a bulldozer, I don't know, if you were to push it, that would be force, like a physical force. However, when chains or ropes are involved in pulling or holding up something or maybe tying it down, ropes and chains apply the same force, but it's called tension because it's not like applying the force itself, it's just keeping it there with the tension that is in the rope. So that's important to point out, just to make sure everybody understands the meaning of tension. So one rope has 25 newtons, the other has 40. And this one, net force equals to ma, but also, so sometimes we have, or most of the time, force vectors are at angles. They're not strictly straight up or down, side to side. They're at some angle, theta. That's when you split into the component vectors, x and y, and solve that way. However, when the forces are already perpendicular, like so, we can write out here, to be extra clear, the force in the x direction is 25 newtons because this one is going in the x direction, and the net force in the y direction is 40 newtons because that rope is only going in the y direction, this one. And when you want to get the magnitude of the net force, and the forces acting on each other are perpendicular, you take the magnitude, which is the square root of force in the x direction squared plus the magnitude of the force in the y direction squared. So for here, if you plug in the values, you get 40 squared. Well, it doesn't matter which order you put them in here. 40 squared plus 25 squared. And then you take the square root of that, which should come out to 1.2 meters per second squared. And that is the answer A, which we see here. Answer A is 1.2 meters per second squared. So that one, do you have any questions on this one or any of the concepts? If you don't have any questions, I'll just move on.
Excuse me.
Oh yeah.
Excuse me.
Mm-hmm.
Okay. I was asking, you took the square root of this after adding the squares together, you took the square root and it gave you this.
Mm-hmm.
Okay.
Yeah,
Okay.
that's. Let me pull out my textbook, because I don't really have like a name to say this is the XYZ theorem. I just know that when you have two perpendicular forces, that is how you take the magnitude of them. Uh, that's how you take the magnitude of any two forces. And I'm sure we'll come to a problem later where we're dealing with an angle. That's what I was talking about here. Like if these two. Oh yeah, actually, I believe the last question on this quiz is like this. Like if you have like a box here, and it said like, oops, it said like a box is hanging from two ropes, and the two ropes are at an angle. Um, and if it were to ask what's the magnitude of the force on the box,
Okay. Okay.
you would split these vectors, add them into the x and the y, and you still use this. You just have to split the vectors first.
Okay. Okay. Yeah, I got you.
Good. That's great. That is wonderful.
Yeah.
So I will erase this and move forward.
Mhm.
That one was pretty good. So now we have number two on chapter 5, quiz 2. Which was 30.61 kilogram mass cross. Notice the rope makes an angle of 30 degrees above the horizontal. Tension the rope is 100 newtons. What is the normal force of the floor on the box? Okay. Okay, so I don't believe I've worked this one out. That's okay because I can work it out now. And if I come to an issue, I will just search it on the internet and see what that has to offer. So the first thing you want to do in these questions, like Dr. Wadahu always says, is to try to imagine what's happening, try to draw, at least at first, if not a free body diagram, just draw a type of diagram. So first we have a box being pulled across a level surface. So level, it's not inclined, it's not an angle, it's just level. And we have a mass here that is 30.61 kilograms. It's being pulled across with a constant velocity. Now that is important because if it's a constant velocity, that means that there is no acceleration.
Okay.
So as we know in our net force equation, F net equals ma, well, if there's no acceleration is equal to 0, that means that this is equal
What
to
is zero?
0. That's a
All right.
theta, 0. That's correct. Absolutely correct. Notice the rope makes an angle 30 degrees above the horizontal. And the tension is 100 newtons. What is the normal force of the floor on the box? So the normal force, for starters, is this box weighs some type of mass, mg. M being the mass, g being acceleration due to gravity. The normal force is always what does the floor or the surface exert back up on the object to keep it up. So normal force, if there was no rope here, imagine this rope is not here. If this box were just sitting here, N, the normal force, is equal to mg. However, that is not the case when there is this rope pulling here, because it's pulling up and away. That means it is pulling some of the, it's doing some of the normal force's work. It's pulling up, it's kind of helping it out. So the normal force, I believe, let's just do a quick little D, answers 250. So newtons, so let's just do that really quick. What's 30.6 D1 times 9.8? 299, essentially 300. And as you can see, the answer here is 250 newtons, but mg equals 300. So as you can see, the normal force with this rope acting on it, kind of helping pull it up, the normal force will be less than this 300 because of the rope. Mm-hmm. So let's resume. The tension of the rope is 100. What's the normal force of the box? So first, we want to break down our force vectors into their x, all the x acting on this box and all the y acting on this box. So in the x direction, there has not been signified any friction here going in this direction, so there's no friction. The only force acting in the x direction here is the 100 newtons of the rope times cosine 30. Now, I just want to explain really quick again the splitting of vectors. You may understand, you probably understand, but for those that may come back and watch this recording later, very important. I'll write down here something. Splitting vectors. So let's do this one at 30 degrees. So when I took this class, I was like, how do I know when to use cosine, when to use sine? Well, at first I just memorized it. I was like, okay, x corresponds to cosine, y corresponds to sine. Okay, I can memorize that. But sometimes, depending on where the angle is, it is not always the case. So it's important to try to understand why we use sine and cosine. So quickly, I'll draw this little diagram. Here, what we're doing is we're splitting this vector into the x component and the y component. And from trigonometry, you probably remember sine is equal, sine of theta is equal to opposite over hypotenuse. Mm-hmm. So here, if you imagine, for the ease of this diagram, move this y over here. It's the same exact length, it's just moved over here, so you can see this kind of makes a right triangle, and you can use trigonometry on it. So you have this angle here, you have this 30 degrees, and we also were given 100 newtons of force. And if it's not given in newtons, mg, but that's for the sake of right now, just keep it to 100 newtons. This 30-degree angle opposite is this y component, and the hypotenuse is 100. So we would write this as sine of this 30 degrees is equal to the y over 100. And then to solve for y, you multiply out the 100, and that is where 100 times sine 30 comes from, because you were trying to look for the opposite.
Okay.
Good. So that makes sense?
Yeah.
Great. That is wonderful. Wonderful, because I had issues with this myself. There's absolutely nothing wrong with that. Likewise, cosine of this theta, now we're looking for the x of this. We're looking for what's over here. So as you remember, cosine is equal to adjacent over hypotenuse, of which this x is to the adjacent side of this 30-degree angle. And we get x, imagine this is cosine 30, x over 100. And likewise we did for the y, we multiply by 100, and the x, the force in the x direction is equal to 100 times cosine of 30 degrees. So just a quick explanation of why we use particularly the sine and the cosine for these respective vector components. Very important to understand that. So using that knowledge, that is why we did in our accounting for all the forces acting in the x direction, we pretty much just have this x component of the rope that's acting. So we have only this and equals to ma. And like we said up here, since there's no acceleration because it's moving at a constant velocity, we say this is equal to 0. And then we do a likewise process for the y forces. Now here we have a little bit more to deal with. We can see that in the y direction, and I forgot to add, I'm using upwards as positive and to the right as positive. This is how you define your signs, and like if you were to have something acting behind, you would subtract. Something adding to the right, add. That's I forgot what you call it, kind of the syntax, how you decide to add or subtract in these force equations. So for the y, we have normal force acting in the positive direction, up. So we have positive n, we have negative mg, because it is pointing downwards, it's pulling downwards. And we also have the upwards y component of this rope. This rope right here, like we saw, has a positive y component of force. So we add 100 sine 30. And again, this is constant velocity.
Acceleration.
Right, exactly. And the box on the y direction is not, it's set, like it doesn't say it's moving up or down, so we assume that it is just staying on the ground, so also there it is equal to 0. So what do we do from here? We solve. So if we're solving for n, we want to keep it on this side of the equation, equals to mg, and we're moving b's over to this side of the equation. So I'm just going to write plus mg. Now we have positive mg minus 100 sine 30. And we plug in, m is 30.60 kilograms. Wow, I just wrote that 3 wrong. 30.61 kilograms times g, the force the acceleration due to gravity, which is 9.8 meters per second squared, minus 100 cosine, I'm sorry, sine, excuse me,
Yeah.
drink some water. 100 sine 30. And I'll just solve that out really quick on my calculator. Always make sure that you were working with the proper degrees or radians. I just had mine set to radians. Make sure you work with degrees here. Times. And this equals out to our answer of 200, well, okay, from the calculator, I got 249.978, but that pretty clearly rounds to 250 newtons, which is our answer. So that means that we did that properly. Goodness. And as we can see here, answer D is correct, 250. So that is how that one is worked out.
Thank you.
Oh, yeah, no problem. Yeah, so you understand any questions on this?
Yeah, I got you. I saw where I missed it. I didn't. I didn't consider the 100 sine theta, the y component when I was doing
Uh, that makes sense. That's
yeah. I
definitely
didn't consider that. So I just went ahead and wrote 300. I said n is equal to mg. So I just went ahead and wrote 300. I didn't consider the 100 sine theta. Okay.
right.
Yeah.
So you probably chose A here.
Yeah,
This
I
300.
chose a, I missed it. Oh my God.
There is absolutely nothing wrong with that. I, you, you know, I don't even want to go into the grades. I've made the highest of highs and the lowest of lows. That is just how physics is. There's absolutely nothing wrong with that. As long as you understand now before the test, I believe the
Yeah.
test is Tuesday. So, and questions like these are definitely on the exam. So, very good that you understand now. So with that, I will move on to the next one. Is okay if I clear?
Mhm.
Okay.
Yeah.
So the next one, to investigate one of Newton's laws, he decided mass system. Okay. My first thought when I read this is like, this isn't very clear. Like, I don't have a clear mental picture, like right off the bat. But if you take even just a second to think about it, um, I believe I understand what's going on here. I'm going to, let me see. Okay. So to investigate one of Newton's laws, he designed a mass pulley system in such a way a 10 kilogram mass and a 2 kilogram mass are connected by a light string over a massless frictionless pulley. If g equals to 9.8 meters per second squared, what is the acceleration of the system when released? Okay, so first you might be like, what the heck is going on here? But you can use some context clues. So for instance, he's giving you g equals 9.8, which you should know is the acceleration due to gravity. Now, my first thought was, I don't know why, this just doesn't make any sense. It's just that my first thought was like, okay, if we have like two masses and this is the pulley in the middle, we have two masses, gravity isn't really doing anything here. These are not going to move, obviously, because they are two mass is just sitting there on a pulley. So that's obviously not how this looks like. Since he provided acceleration due to gravity, it must play some role in here, of which I believe is a situation that looks like this. A box is sitting here, pulley is here, and they're attached by a weightless, frictionless string, and a second mass is hanging here. And that's why we need the G. Okay, so, and what is the acceleration of the system when released? Okay, so this one is a 10 kilogram mass, and this one is a 2 kilogram mass. And, okay, so, and we have the tension going, well, this one is very light, and this one is heavier. So,
I think they should be flipped.
yeah,
The masses.
that does definitely make sense that the heavier one would be hanging down. Thank you for that. That's a very good point. Thank you. So this one should be 2 kilograms, and this one should be 10. And now we have this tension definitely pulling in this direction here. And for this free body diagram, we have one pulling up here. And this is why it's important to draw free body diagrams. I'll label them 1 and 2. 1. We have the free body diagram for this box on the counter. That would be this tension in the rope going this way. The mg going down like this, and the normal force of the counter going up like this. These are all the forces that are acting on this box up here. Now for this one, we have one less force acting on it. We purely have the tension in the string holding it up, not letting it fall to the ground, and we have the pull of gravity pulling it down, which is why we need the G that he gave us here.
Okay.
So now what do we do? Now, I, again, have not solved this one out, but I've solved problems very similar to this, so I'm just going to solve it and hope that we get the right answer from my knowledge. So, in the x direction, actually, you know what, before I even start, let me pull out some old notes, because I don't really want to waste time getting things wrong. I'm pretty sure I know what to do, but I just want to ensure. Okay, so what we do is we write these force equations for each of the objects. So this one is the 2 kilogram, this one is the 10 kilogram. So for the 2 kilogram one, we have the tension. Now, this says, what is the acceleration of the system when released? Since this rope here on the first box is not at an angle up or down, it is perpendicular, it has no effect on the normal force. So in this case, N is equal to mg. And that force is not really, this normal force, gravity force, is not really affecting this motion. All we really have that's affecting the motion of the 2 kilogram box is the tension of the string. That is what is pulling it forward. And if we have positive T, positive tension, equals to MA. So right off the bat, we can just say 2 kilograms times A. So this is for the 2 kilogram box. And it is in the X direction because it's the only type of motion that it has. For the 10 kilogram box, which is moving in the Y direction solely, it's not going side to side ever, it looks like this. So as we see from our free body diagram, this is why Dr. Wadahua might have said, I can't remember exactly if he said, but he probably said, draw the free body diagram, then write the force equations in the direction of the motion. That's so important, I'm even going to type it out. In the direction of the motion. Because that's kind of what I was explaining earlier. In this first box, the normal and the gravity force don't do anything for the motion. The only thing that's in the direction of the motion is this t. So that's why it's the only thing in this equation over here. Now, for the second box, what's in the direction of the motion? Well, the direction of motion that this could move is either up or down. And so we need to account for both of those forces that are acting in those directions. So we have, if we have said positive is up, we have the tension acting in the positive direction. So positive tension again, minus mg, which I'll write out just right off the bat. M is equal to 10 kilograms. mg, and g was given, or you should already know, is 9.8 meters per second squared. And this is set to equal to ma, which is 10 kilograms again, times acceleration. So, what is the acceleration of the system? You solve for these two equations, you solve for A. So, and another important note to note is that since this is a massless frictionless pulley and a massless frictionless string, these two tensions are equal to each other.
Okay.
So these two tensions here, these values here, are also equal to each other. So what can you do to solve for A? Dr. Wadahua solves sometimes a shorter method, which I do know how to do myself, but honestly I don't feel comfortable explaining because heaven forbid I say something wrong. So I'm just going to solve it also just as quickly as just solving substitution using system of equations. As we see here, t is equal to 2 times a, and if we plug this into this equation, we can just say the same t here, so 2a minus, let's just multiply this right off the bat, 10 times 9.8 is 98, equals 10a, 10a. And if we subtract 2a, we get, this is 8a, and this is negative 98, and multiply out the 8. So a is equal to 12.25. That is not the answer. The answer should be 6.5. Okay, what did I do wrong? Okay, let me write out the answer I got. I got 12.25. Maybe I had the concept of this wrong. Let me quickly search this with Google. And when this happens, this is not cause to freak out. You just, if you're on a quiz, I would definitely freak out. But I don't know. Let me think for a moment. He's using gravity is equal to 9. He should be using 9.8. Um, okay, so I'm looking at what he wrote. I've never seen this kind of notation before, like m1 minus m2 over m1 plus m2 times g. I'm not familiar with that. Let me look at another one. Okay, it's 10:20. I have this scheduled until 10:45, so I have a second here to sit here and try to see. So just a quick question. Did you get this right on the quiz? Excuse me, you who's there, did you get this question right on the quiz?
Yeah, I heard you. I'm sorry. I muted myself.
Oh, that's
Uh,
okay.
uh, yeah, as I was saying, I can't remember, but I'm looking for I'm looking for my worksheet if I could find it, because in the test I got 10/25. So I'm not. Uh,
10/25, that's interesting. Um, I have to
telling
admit,
you.
yeah, I have to say I've never seen this right here. That would be something that I need to look into because I only know how to solve it like with his equations. This is something I need to look into. If I can't figure this out right now, um, I will look at this after and figure out. Because, okay, let me look at one last source. So they say that the formula for acceleration of system is this expression right here. Obviously, Dr. Watt doesn't teach this because I've never seen it before. I guess I just need to go back and redo this. I mean, okay, I'm not overthinking it. There was no theta here. It's not like this is on an incline. Um,
Okay, excuse me,
mhm.
Grace.
Yeah.
Um, yeah, I think I got this. I've seen it. I've seen the diagram I drew. The diagram I drew was a pulley. This 2 kilogram was hanging. It wasn't on a table. It,
Hmm.
it was hanging. You understand?
Hmm.
So because it was hanging,
Oh. Okay, so like this, like a pulley, and they're both hanging?
yeah, that's the diagram I drew. And, yeah, I can see. Yeah, I got this one. 6.5. Yeah,
Okay, well,
awesome.
that's great that you got it right. I'm very happy about that. Um, That is wonderful. Okay, because that's what I was concerned about at the beginning. I was like, this doesn't really give a whole lot. But then again, we cannot assume what I did was wrong. We cannot assume that there was a table here because there is no mention of a table. There's no mention of a surface. It just says that it's two masses by a string over a pulley. So that was very smart. I'm very happy that you got that correct because I did
Yeah,
not.
yeah. He
um,
didn't say it, so it would be confusing. He didn't say the whether it was on the table or not. Yeah,
right. That's exactly right. And that is exactly the kind of things you do not want to assume. You should never make assumptions, just like I
yeah.
did.
It's dangerous.
Exactly. That is a very good thing to learn. So let me see if I can just solve this out really quick like this. Well, if they're both hanging like this, then they both have free body diagrams that look like that. And this one is T. So I'm doing T minus mg for the 2 kilogram. It's to MA. And for the 10 kilogram, very similar, 10, 9.8 mg equals 10A. Um, I'm thinking, so since I have a second shot here, I'm going to try to solve like I know how Dr. Watt does and see how if I get the same answer. I should. If you subtract these two, this goes away. This and this. Then we have 2 times 9.8.
No, excuse me, Grace.
Mm-hmm. Yep.
I think your second equation. I
Mm-hmm.
think you missed something. This is supposed to be negative.
That's correct. I did originally have this. The tension, do you mean, or this right here?
This one, like what doctor told us in the class, um, and what I also saw in the textbook. I said because this mass 10 is bigger than 2, it is normal, and they are on a frictionless pulley. It is normal that
Right.
uh, this one pulls down the 2, the 10 pulls down the 2. So it will be 10 mg minus T. Then since the tension here is pulling down it is pulling up the 2 kilogram, then it will be T minus 2 kilograms. So the direction of motion is, yeah, exactly.
Exactly right. Here you are up here teaching class today. This is wonderful. I'm very happy. I yeah, I haven't eaten breakfast yet. uh,
Me too.
so wow. Okay, this is wonderful. I'm very very happy. You definitely caught that. That is absolutely correct. Absolutely. The direction, and that's what I was just preaching earlier. You gotta do what you preach. Um,
Yeah.
you gotta write it in the direction of the motion. So it's very, very good thinking. The 10 obviously is heavier. It's going to be pulling the system down.
Mhm,
It will be moving downwards.
mhm.
Its direction of motion, this will be moving up. direction of motion. So for this one, it is moving upwards, so this t is positive, this is negative. However, just like you said, here, let me erase this. Just like you said, this second one's direction of motion is in the negative, which means that the t is going up, so it is negative in the direction of the motion, and this mg is in the direction of the motion, so we add that. Absolutely correct. Wonderful. That is amazing. I'm very happy.
You're welcome.
Thank you. Yes, thank you. So, okay, now let me try. Okay, so I thought that was different. I was like, you don't subtract them, you add them, but I need the t to cancel out. This is how you get that to happen. So this is the fast or the faster, or just, I don't even know if you want to say fast. It's a different way to try to solve. You add the two together, so the t's cancel out. You have 98 minus 2 times 9.8. And you have here, I'll add 12a. So if you get from this, the 98 minus 2.98, you get, or should get 78.4. And if you divide that by 12, okay, there we go. Then you get a is equal to 6.53 repeating, or just 6.5 meters per second squared. And that is your answer. So wonderful. Thank you for your help on that. I greatly appreciate it.
Me too.
That is a lesson, a wonderful lesson to be learned here, is that never make assumptions. This question does not mention a table. So I should not have drawn that. It is exactly as you said, just two things on a string, on a pulley. That's all you can get from this. And you should be able to get 6.5. Always put them in the direction of the motion. Like here, these are very all good, important points. Wonderful. Okay, so clearly you very much understand that. I'm very happy for that. I will clear this then and move on to the next one. Let me see if I had figured
You
this out.
see this one, rest on a frictionless surface. So this one,
Exactly.
yeah, this one is
Exactly.
resting. Mm-hmm.
So this one is on a surface. Now we are given the data. We don't have to assume anything anymore. Okay, so a 50 kilogram blob rests on a level frictionless surface and is attached to a light string to a 5 kilogram hanging mass, where the string passes over a massless frictionless pulley. G equals 9.8, tension of the connecting string. Okay, so
You know why I did poorly in this test? Yeah? Let me tell you why.
mm-hmm.
I only read to where Dr. Watt taught us. Before this test, sorry, before this quiz, we have not come to this side of the topic. Resting on a pulley, frictionless mass, all this stuff. We have not gone. As a matter of fact, we just finished projectile and did introduction to resultant forces.
Oh, I see.
Before we took this test. So I was kind of I tried to use what he told us in projectile. I'm not saying that he did wrong. No, but because he clearly stated that the quiz is going to be on F equal to NA. So it was my responsibility to look or study beyond where he taught us. So I learned a big lesson from that. You
Right.
understand? hmm
I
So
see.
hopefully, yeah,
Mhm.
hopefully next this exam, hopefully I'll do better.
Well, that's certainly very responsible. That's very true. Uh, and I had to come to that realization that these classes, are my responsibility. And now Dr. Watt is pretty fair. Now,
Yeah, he
also,
is.
he is very fair, so I may ask him just very casually if he would, because he normally does not, he's very usually good about not giving quizzes or tests over material that he has not covered in the lecture. However, this is the second start class, and like you said, um, it is your responsibility to, see the material. Let me write a note before. But also, like I said, Dr. Watt is usually very good about not having quizzing over material before it's given in a lecture. So honestly, I'm at a loss. I don't really know what to say. I mean, he knows what's on the quiz, so and he gave it. So you know, if he meant to give it, even without going over everything in the lecture, exactly what you said, responsibility. That
Yeah,
yeah.
yeah. I'm not saying he did wrong. No, the truth is, I actually like him. Let me tell you why.
Hmm.
His style of teaching and is good. He explains. He makes us. He wants us to understand what it is, and he tells us that if we follow these steps, we won't get it wrong, and it's true. I actually like his class. Understand? So that's why I said um, it was my responsibility. Since he already stated that this quiz is going to be on F equal to MA, it was my responsibility to look beyond where he taught us. So yeah, he's like he has already giving us what is going to come out. So I have to take it as my own duty to go beyond where he taught us. And the truth is, these questions are cheap. Do you know why? Because I've read his handouts, his book, his materials, and the textbooks. Looking at these questions now, I'm not scared. You understand?
Yes.
Because yeah, I'm not scared because I have read his book and his materials, and his material covered these questions. So where I failed my part, it was I failed in my own part to look at the whole material on F equal to MA. I was just looking at where he maybe explained to us before the class ended. But it's okay, it's fine. I'm good. I'm
Uh
okay.
yeah, I completely understand what you're saying. And first, I just want to say you have a very good outlook. You have a very that kind of outlook is what's going to have you be successful in this class. I can tell you right now, um, a lot of students. Let me just